Hello, ladies and gents. This is one of my favorite topics to talk about is momentum and impulse. One of the things I love about momentum and impulse is you really know this. You woke up this morning understanding this, but you did not probably know that there was an equation that described it. We're going to start with the definition of impulse. Impulse is the idea that if you want to change the momentum of an object, you've got to apply a force for some sort of period of time. That makes sense, but there is actually an equation that describes that, and it's called impulse. Impulse is the force applied for a period of time that actually changes the momentum of an object. So the equation for impulse is force times the amount of time that force acts. Force is in newtons. Time, of course, is in seconds. And impulse is a weird and wacky little thing. It is a vector, and it is a vector because of the fact that forces come in a specific direction, and it is very closely related to momentum. The units on impulse are the Newton seconds because force is in newtons, time is in seconds. Now the symbol for impulse is either a capital J, which again I find confusing because J usually means joule. So I have a tendency to use IMP for impulse because, again, I want clear communication. Impulse is part of something that is bigger, and this is called the momentum impulse theorem. Put a box around this, copy this down. This is just a really powerful and useful little equation. And it's different from most of the equations we've had so far because of the fact that it has 1, 2, 3, 4 sections. Why it has 4 sections are all 4 of these things happen to be equal to each other. If you change the momentum on an object, that is going to affect its mass and velocity, which is caused by a force acting for a period of time, which can be called impulse, or the change in impulse on it. Now, when we start doing math problems, you have to pay attention because you can be given any 2 of these things. So in a problem, it might say, what impulse causes a mass to change by so much velocity? So you actually can take these 2 pieces, set them equal to each other, and then do the math. In another problem, you might be told that what is the change in momentum of an object if a certain force is applied for a certain amount of time. And then these 2 pieces have to be set equal to each other. So you have to be a little flexible, and you have to look at this equation carefully when you start doing the math. The other thing that's kind of nifty about this momentum impulse theorem is that this is how Newton originally wrote his second law. You and I are used to Newton's second law being force times mass times acceleration. Well, acceleration is defined as a change in velocity and a change of time. If I transfer that into F equals ma, I end up with force is mass times a change in velocity divided by a change in time, or force change in time is mass change in velocity. Remember I said a while back that momentum does not have its own units. Units for momentum are kilogram meter per second. And why doesn't it get its own name? Well, probably because of the fact that it really is a different way of spinning or looking at Newton's second law. It's a principle, meaning that it is got limited use, collisions, explosions, and things like that. Before we do math with the momentum impulse theorem, I want to talk about this equation. And remember I said you know this equation when you woke up this morning? There's so many places out there in the world where this equation explains why you do what you do. First off, let's talk about follow-through in sports. Some of you have played an awful lot of sports either on teams or privately, and some of you are not sporty at all. But if you've ever swung a bat or a tennis racket or a golf club or a pickleball or whatever, your coach usually says, make sure you have good follow-through. Well, what does follow-through give you? What follow-through gives you is a slight increase in time. Tiny, tiny fractions of time. How much time do you get when you have a really great follow-through on your swing? Little bits of time. We're talking tenths of a second or less that you actually have in contact with the ball. Well, why is that to your advantage when you're playing a sport? Because that small change in time is going to make a big change in velocity. Because if you look at this equation, what's the force? Well, when somebody comes up to bat in baseball, the force is the force of the athlete. That's already been determined in the gym and by how much you've worked out, and everything is determined before you get there. The mass, this is the object that's being accelerated. In sports, this is typically going to be a ball or a puck. So when you come up to swing, if you can have a small increase in time of contact with the ball, you get a much bigger velocity. So what does that give you? That gives you a home run hit. That gives you a wicked serve that is really hard to return. That means the golf ball is going to go even further. And your coach knew what he or she was talking about when they said, make sure you have good follow-through. Here's another example. If you increase momentum by increasing contact time, short barrels and long barrels. Now, these pictures are both of Civil War era cannons. If you have a short cannon or a long cannon, what actually causes the explosion? What's the event that makes the ball fly this way and the cannon move back that direction? Well, it's going to be an explosion of gunpowder somewhere inside of the cannon. If you have a short barrel, the amount of time that the expanding gases have time to actually accelerate the projectile is going to be quite small. What that means is the velocity is going to be quite small. If you have a long barrel cannon, what that means is there's more time for the gases to accelerate that projectile, and it's going to come out with, if you have bigger contact time, with a lot bigger speed. So you use a long cannon if you want to launch a projectile with high velocity, which means, as we know from projectile motion, a long distance. These short little cannons in the Civil War, they were very often used inside of a fort, and the purpose was to shoot over the wall and just keep people from attacking in your fort. It was not to hit from one side of a big battlefield to another. This can also be used if you start talking about people who do long distance shooting. If you're going to try and go deer hunting and you're going to try and shoot a deer that's 100 yards away, well, 100 yards is 300 feet, and that's a pretty decent shot. It's the other end of the football field. You're going to need a long gun. Why? It's going to give you enough velocity so that the projectile will go that far. You do not have a little 2-inch barrel that you are going to try these long distance shots with. All right, let's take this equation and let's turn it on its side. So here's what we've got. If I have force change in time is mass change in velocity. If I want to make impact force very, very, very small, what I can do is I can make the time of impact big, and that's going to make my force applied very, very small. Let's go through a couple examples. Airbags are a fabulous example. There's some sort of a little car crash. The mass is the mass that is being decelerated or slowed down. This can be your body, your head, your automobile, whatever. But if you're not going to change in the middle of a collision. It is what it is. The mass of your body, the mass of your car is what it is. Change in velocity. Let's say your car is going from 55 miles per hour down to stopped at 0. So in the middle of a collision, you can't change that. The mass of the object, the change of its speed when it stops, this side is actually set. But what you can do if you want to make force small is you make the time to stop as big as possible. That's the beauty of an airbag. It takes time for your body to slow down. This is a stunt person jumping into a large airbag. When this person hits the airbag, the air whooshes out in all sorts of sides, and the purpose is to slow down that collision to make the force of impact small and survivable. One of the most in the news in the last couple of years examples of this have been NFL football helmets. Long ago and far away, they just used simple little leather helmets with maybe a little bit of sheepskin padding, and through time the helmets have gotten more and more and more sophisticated. Well, the new modern NFL helmets are this wonder of engineering, and the purpose is to prevent concussions, prevent long-term brain injury to people who play football by taking the collision time and making it huge, because this is the mass of the head of the person who's wearing the helmet. This is the change in velocity. They're going from whatever it is down to stopped. And in the middle of a collision, if you want to protect somebody, this is set. You can't really change that. But you want to make this small, so you make collision time really, really big. So how do they do this? One, there's a load shell. The outside surface actually helps distribute the load, distribute the force all over. There's a core layer. All of these little pockets in here, this is a crumple zone built into the football helmet to slow down the amount of time it takes to stop the head. There's a plastic shell sandwiched between the soft layers to just help protect the skull, and then the foam lining is to help distribute the force throughout and around the head so you don't get one spot that gets really whacked. Plus extra padding in the chin straps so that people do not get a lot of force on their jaw, which could break a jaw, which would be painful and no fun. There's so many examples of this, making time big to make impact force small. A boxer rides with the punch. They don't just sit there, they ride with the punch. And when they ride with the punch, they increase their collision time fractions of a second, tenths or hundredths of a second, very, very little. But by doing that, the force of the impact is less. Many of us have played the old toss the egg game, where you stand next to somebody, you toss an egg, then everybody takes a step back, toss an egg, and you know how to catch that egg? When you catch the egg in your hand, you then you ride with the punch. You absorb some of the energy with your hands to keep the egg from being broken. When you jump off of a chair, you bend your knees so that you can distribute that force over a much bigger time. And by doing that, force on your body is much less. If you talk about NBA basketball courts, they are not just a concrete floor. They are a complicated construction of all sorts of different layers of laminate, each one designed to absorb impact. Hey, you do not pay these guys multi-million dollars a year and then send them out to play on concrete where their knees are going to get shot because there is nothing to help absorb the impact. If you have ever done gymnastics or dancing or anything like that, you don't want to do this on a concrete floor. This happens to be a picture of a portable ballet studio floor. Same thing, lots of layers, lots of squish. Again, the purpose is to protect the athlete. My cat, this is not my cat, I don't have a picture of her in here, but my cat has a brain about the size of a walnut. Okay, she's a cat, she's not that bright. But when my cat gets on the kitchen counters, which she's not supposed to, but she's a cat, she gets on the counters, and she wants to jump down off the counters, she will walk from one end of the counter over to the place where there is a rug, and she'll jump down on the rug instead of on the hardwood floors. And why? Even my little walnut-brained cat understands that if she makes collision time bigger, the impact on her body is going to be less. See, my cat knows physics. One more way we can take this whole thing and flip it on its ear is we can increase force by decreasing collision time. And here's how we're going to do that. Now, I have never played hockey and I've never done martial arts, but I've had gobs of students through the years who have done both. And all of them have said that if you take time and make it really, really, really small, you can increase the force. Classic example is a slap shot. Lots and lots of spring potential energy are held in this hockey stick, and then you release it all at once in a very quick little shot, lots of force given to the puck, and you end up with a greater acceleration on that puck. Many of my students who have done martial arts have all told me that when you do some sort of a martial arts hit or kick, you do not shilly-shally around. You want to make this as fast as possible, because this is the mass of your body part, your hand, your foot, whatever. The change in velocity is the change from where you start to how it ends. And if you really want to impact whatever you're hitting, if you can make the impact time small, the force of impact is going to be much bigger. The last example is not a happy example. It's a very sad example, but to prove a point. One of the reasons we have airbags, one of the reasons we wear seatbelts is because of the fact that if you take a human, this happens to be a dummy, crash test dummy, and you have them stop their body in a very short period of time, the force on them is going to be huge and potentially can be lethal. And we want to make that collision time big so we can make that force small. All right, that'll do for this time. We'll come back next and we'll do a problem.